All right, so today we are talking about isometries. Okay. So our objectives, we're going to define isometries and recognize transformations that are isometries. State 6 preserved characteristics of isometries. Define and perform glide reflections. This is probably the first time you've heard of those. And apply isometries to solve real-life problems. So it's a glide. That would be a translation. What is a glide? A glide reflection is where you translate and reflect. You're going to glide it over and then reflect it. It's just a two-step. Yeah. All right. So isometry, first of all, is a transformation that preserves distance. All the ones that we've done are isometries, right? Because in Greek, okay, they're also called rigid transformations. We start there. Oh, there's our timer to pray. So let me pause it and okay. So isos is Greek for equal. Metron is Greek for measure. So isometry literally means equal measure, right? Everything in the shapes when we're doing them stays equal measure. A dilation is not an isometric transformation, okay? But the ones we've done so far are. So transformations that are isometries are the reflection, the translation, the rotation, the identity transformation. What was that one?
Changes its identity.
No, remember we maintain its identity. It was either a 360-degree rotation or any rotation, any two rotations that were a combination, like that combined, we call them a composition, that equal 360. So it could have been a 270 and a 90, or an 180 and another 180. Okay. So that goes to any composition of isometries. So you could do 3 or 4 of them, and you're still going to maintain that same shape. And the new one we're talking about today is the glide reflection. Okay. So there are 6 characteristics that are preserved or invariant in isometry. So the 6 things that don't change. It's kind of hard to see up there. So distance is one of them. Okay, we preserve the distance. We preserve the collinearity of points. What is collinearity? That was close.
A
A line?
line. Stays the same.
The line stays the same. The points on the line stay the same. Okay, so they're the same distance apart. They're still on the same line. Okay, sorry, that they're still on the same line. Then the next one is betweenness of points. So the distance between the points when we move them stays the same. It's consistent. Our fourth one, angle measures stay consistent. Even if we reflect them or whatever, the angle measure stays consistent. Okay, we don't lose that. Parallelism. What do you think that means? What's the root word in there? Parallel. Okay, so these lines were parallel before. When we did the transformation, they remained parallel. Okay, so we're not losing that. We're keeping that. And the last one is triangle congruence. What does that mean?
The triangles are congruent.
The triangles are congruent. Okay, and it doesn't matter what shape it is. Any shape will remain maintain its congruence. Okay, when we do any of these isometry transformations or rigid transformations. All right. Questions? You're such studious students. All right, glide reflection then. This is that new isometry. It is the composition of a translation followed by a reflection. I know. I'm going to have to close it out in a minute. In a line parallel, so this part is important too. It's in a line parallel to the translation vector. Okay, I know, right? It's pretty awesome stuff. Let me close my board here. Okay, all right, so there is an example of this glide reflection over here. Okay, so in our glide reflection, this is our original shape. What does it have to do first? It has to glide, right? Or do a translation. So it translates. So that's step 1 there. What's the second step? The rotate. Okay, so it rotated up here. So that's step 2. What was the key to the rotation? What did it say? The reflection is what?
I don't know.
In the definition, a reflection in a line
Parallel.
parallel to
The
translation vector. Okay, so this is the translation vector, right? Like we slid it over here. So we have to rotate it or reflect it across a line that's parallel to the translation vector.
Can translation only go straight or can it go diagonal? Or like, can it only go horizontal or can it go diagonal?
It can go horizontal and vertical, and it can't go diagonal. We're going to focus on like horizontal and vertical ones, not diagonal ones. That will come in like later time of geometry. I don't know. So every rigid transformation within a plane can be described as the result of one of the four transformations. Okay, so every single one can be described as a reflection, translation, rotation, or a glide reflection. But again, a glide reflection is kind of cheating, right? It's two. It's a translation and a reflection combined. Okay, we can talk about that later. Isometry theorem then, the one theorem from this chapter. Every isometry can be expressed as a composition of at most 3 reflections. I feel like that's not supposed to say reflections. I feel like it's supposed to say transformations. Like I think I have a typo. No, it does say 3 reflections. Every isometry can be expressed as a composition of at most 3 reflections. Okay, I'll leave that there then.
Okay.
All right, example 1. It says find an image of triangle RST after the glide reflection defined by the translation vector 5, 0, and a reflection in the line y equals 0. Then write the mapping rule for the glide reflection. So there's quite a little bit there, but I'm going to move it on up. Okay. All right. So we know it's a glide reflection. What is a glide reflection? What 2 parts does it have? Okay, not the rotation. The reflection. I was like, it's in the name. So it has the glide first, and then it has the reflection second. The vector tells us how to glide it, right? All right, so we need to transfer RST to our graph. So what's point R here? 0, 3. Okay, so on your graph, let's put 0, 3 for our R. What's S? Negative 1, 1. And where's T? Negative 4, 2. Okay. 1, 2, 3, 4. Okay, so there is our original TRS. So we want to use our vector 5, 0. What does the vector tell us? That 5 and the 0.
It goes over 5, doesn't go down any.
Okay, so the first number is always the x and y, how many it goes over. So it's going to go over right or left since it's a positive 5. Right. And the 0 says there's no change on the y-axis. So from each point, we're going to go over 5. 1, 2, 3, 4, 5. And label it with your prime. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Okay, so I'm going to put step 1 here actually in red.
Reflection would be on the y-axis.
Okay, so here's the thing. Let's do this. Remember, my vector was this way. I want to glide or reflect in the y equals 0. This is my y equals 0. Are those 2 lines parallel? The vector and this, they are parallel, so we're good to go. We can reflect then on those because they are parallel. Okay, so how do we do the reflection?
I did it, but I don't know how to explain it, but I did it.
Okay. To remember to do a reflection, we want to know how far is R from the axis? 3. So then we need to go down 3 and put our R prime prime. S is how far? 1. So we go down 1 and we put our point there for S prime prime. T would be 2. You got it. All right, that's kind of hard to see, so I'm going to make it, I'm going to connect it in pink here. You did it! Woo woo! Glide reflection, 2 steps there. I know, it was awesome. You guys were. It looks really messy, doesn't it? Yeah.
Yours does.
Yours doesn't look so messy?
No, because I think it's because it's all one color.
Okay. Gotcha. Well, I try to make a different color so it stands out a little better, but.
Mine's all in purple and I didn't do all those weird lines that you did.
Okay. That works out. All right, next up then we have the mapping rule. Remember, do you remember what the mapping rule looks like?
Yeah.
We have a point xy, and we need to map it to point P prime, and it's like the x plus whatever and the y plus whatever.
Oh, yeah.
Remember, we have to apply those changes.
But this one is to the P to the prime prime, right?
This one is a P to the prime prime. So there's a couple different ways that you can look at how you're going to get there. You can go P to P prime to P prime prime, and then we can combine those. Or we can look at the actual values and see how they changed. Do what?
Just the whole triangle itself?
The whole triangle is P. It's the original. So it's any point.
How do you measure reflection if every point is different when it goes?
Okay, see, that's what I thought we might have an issue. So let's look at this. So let's look at R.
Okay.
What are the coordinates of R?
The original coordinates.
Original coordinates.
0, 3.
Okay. So what are the coordinates of R prime prime?
5, -3.
Okay. What are the coordinates of T?
4, 2.
And what are the coordinates of T prime prime?
1, -2.
All right, and S, since I didn't go in order.
1, 1, -1, 1.
And S prime. Prime.
1, -1. Or no, sorry. 4, -1.
Okay, so there is a pattern into how each of these changed. Some people can look at the before coordinates and the after coordinates and they can find a pattern.
Yeah,
Like,
y.
what happened to the X? How did I get from 0 to 5?
Every x is plus 5.
Plus 5. Okay, does that work for this one? -4 plus 1?
Yes.
Anybody else say yes? Okay, it's 5. -1 plus 5 is 4. Okay, so that means we take our X value and we add 5 to it.
So would your y value be
So then,
the negative of the number?
does that work? Is it the negative of the number?
Yes.
So 3 to -3, 2 to -2 is a -1 to -1. So then this would just be -y. That's it. So our mapping rule would be, we have our point, which is x comma y, and we're going to map it to point P prime prime, which is our x value plus 5 and a -y. That is your mapping rule.
Coolio.
For you, but what about the rest of you? Does that make sense? Okay, because we're going to continue to work on the mapping, like writing the mapping rules in class. Justice, how do you feel about it? Fine? Okay. Katie, any thoughts from you? No? Are you kind of following along? Okay. Awesome.
At my school, we're learning about, we just started learning about reflection.
Okay, cool. All right, so we ready for the back? There is a back. But see, the next one is we're working on writing the mapping rule. Okay, so example 2. We want to name the isometry used to map each transformation, and write the mapping rule describing the isometry. Okay, so ABC is our original. Okay, then we want to map it to DEF. So this is A. So what kind of transformation did we do there? We did not rotate it. It's in the same. We didn't rotate it. It's
Yeah, rotation.
rotation would turn it.
No.
So then like CB would be vertical if we rotated it.
But if you rotated it 270 degrees,
It would still have a different orientation. Right? So like CB, if I went 270, CB would be vertical in quadrant 1. If I went 270 again, CB would be horizontal, but it'd be in quadrant 4. And then if I did 270 again, CB would be vertical, and it'd be in quadrant 3. I know.
okay, then it's
Lucas, what do you think it is?
What's that called?
We've got translation. They're on the front of the thing. We've got reflection, translation, rotation, or glide reflection. Those are the 4 basics. Okay, I hear 1 for translation. Agreed. Okay, so it's a translation. Okay, so, right, I heard that it was diagonal, so its vector is diagonal. Remember, our vector is how it changes, so we can pick one point and compare it to the other point. So do you want to go, we're going to map 1 point. Which one do you want to take, A, B, or C? A? Okay, so how do we get A to what's its corresponding point? D, right? I heard. Okay. So what did I do? Well, it's horizontal first. This is the opposite of slope. Over 4 and up 2. So if we were writing our vector for that, it would be 4, 2. Which makes writing our mapping rule super easy.
Hey, is there a mapping rule for 2?
That's not our mapping rule. Our mapping rule is always that P, X, Y.
Yeah, but like, you know what I mean. You just put the 4 and the 2 in there.
How do we put the 4 and the 2 in there?
X plus 4.
Mm-hmm.
And Y plus 2.
You got it. That is your mapping rule.
No, this one.
Very nice. All right, so let me erase some of my junk here. This is one of those times I maybe should have made our notes longer so you could have each of the different ones. Okay, so ABC to GHI.
That's a rotation.
Anybody? I don't know why I put 2 there. I meant to put B, but anyway. Anybody agree with rotation?
Rotates 90 degrees.
Okay, so the other thing to help you is like pick a point on there. Like I laid my pin. Okay, I've got my pin laid across here like CB. Okay, I picked a side and I have my pin. If I rotate it 90 degrees, or yeah, is that clockwise or counterclockwise? Counterclockwise. So I'm going to take my pin and my pin is now going this direction. Right? So I picked one part to rotate it and see. So if I rotated it 180, then that AB side would now be this way. Does that make sense? Like I'm trying to give myself a visual representation of what it should look like. So you agree that it's a rotation then. Okay, how many degrees of a rotation is it? 90. All right, excellent. So we've got a 90-degree rotation. Okay, so then we have to look at that mapping rule. So rotations were 10-3. We can use those shortcuts to the mapping rule to help us, like they gave us the mapping rules. Or we can look at the points and figure them out ourselves. It does not matter. It's just if you have them memorized, great. If you don't, then we can look at them. Like B is, what's the coordinate of B?
-3, 1.
I have -2.
-2, 1.
Okay, so I'm going to do this. So we have B is -2, 1, Whoops, -2. And it maps to h, right? Okay, and what's, actually I'm going to put h over here. What's h?
1, -2.
Oh, 1, -2. So that maybe gives you a clue as to what's happening.
Oh yeah, they switch.
Ow, they switch. Okay, so let's try another set, okay, of points and see if the same thing happens. So let's look at C. What's C right now? What's its coordinate? -4, 1. And so C maps to I, so what's I's coordinates? So did the same thing happen? Okay, so what is our mapping rule
You
here?
have H wrong.
Isn't C -5, 1?
C is -5, 1. I don't know, I didn't count them. 1, 2, 3, 4. Ooh, she nailed you all.
Your H is wrong.
Nice catch, Katie. And my H is wrong?
It's
-1. -1. Thank you. Okay. Makes it a little harder or easier, better to see. So did we find all of our mistakes? Okay. I'm going to take the silence as yes. So what's our mapping rule then? Justice, what did you say they did? They switch places. Okay. So our y is here and our x is over here. But that doesn't, we had -2 and the y became negative, right? Because y was 1 and now it became -1. It was 1 on C and became -1. So there you have it. They switch and 1 became negated. So again, you can use the shortcut because that's exactly what it's going to say in 10.3 notes if you had that memorized, or you can always look at your points and figure it out. I know, it's supposed to be C. Lovely, right? Just one more typo. So C, we're doing A, B, C to J, K, L. Okay, I hear reflection.
Oh, y-axis reflection.
A y-axis reflection. Anybody agree with that? Yep. Okay, so we've got a y-axis reflection. Okay, and so then how are we going to find our mapping rule?
Wouldn't it just be...
Okay, hold on. Lucas, what were you going to say?
You can go first.
He's talked a lot today. It's your turn.
That is a good answer, Lucas.
You'd find the line where they reflect maybe.
Okay, so we
It's the Y line, and you would find how far away they are from that line.
okay, so that's how we do it, right? This one is 2, this one is 2. Okay, but how do we write the mapping rule for it? Because remember, the mapping rule is in this format. It's what is the change to the x and what is the change to the y. Okay.
X becomes the X changes, the Y stays.
The x changes, the y stays. Okay. How does the x change and the y stay?
No, they both change, won't they?
I don't know.
No, the Y does stay.
Okay.
Because the X goes from being negative to being positive.
Okay. So he's saying the x goes. So if we look at this, right, we know b is -2, 1, right? Our b is -2, 1. And our k that we're switching it to is a +2, which is what he just said. The x was negative, it became positive, and the y stays. So he just kind of proved what he said. So how do we convert this into the mapping rule?
Is it still Lucas?
It'd be X, Y on the P, and it'd be -X.
You got it. Perfect. Nice work. All right, we'll do D and then we'll stop there for today. We'll save example 3 and 4 for tomorrow. We'll come back to them. All right.
It looks like you're trying to build a
Okay, so how about this last one? We're taking ABC to triangle XYZ. It is a glide reflection. Excellent. Are you guys okay if I erase this? Okay, because I'm like, I need some more room. Okay. All right. So it's a glide reflection. Good. So how?
But instead you go down.
You go down. Okay. How many do I go down?
1 sec. I'll figure it out.
Okay. Justice, how many do you think we go down?
4. It goes down 4.
Because we want to glide it, so we want to slide it down, and then we want to reflect it. Because if we slid it right and then down, it would look completely different. So we go down 4. So 1, 2, 3, 4. Okay, so I'm going to put C prime here. And then 1, 2, 3. Hold on, I think I'm off on my... Yeah, here we go. So there's my A prime, and B prime is 1, 2, 3, 4. Okay, so yes, there's our in-between. And we're going to reflect it now. Awesome. So just out of curiosity, what's my vector here for that glide?
0, 4. Negative 4.
It's 0, right? Because we didn't move it. The x didn't move, and we went negative 4. That's not required, but it might be helpful. All right, then how are we going to find our mapping rule? Nice. The x changes. How'd you get that, Katie?
What?
How did you get that?
I did what we did for the one on top.
Okay.
And how the exchanges changed up there. Negative, positive on here. We moved it over.
Awesome. So our x changes. So we're going to have a negative x. How about our y?
X or y minus 4.
Okay. Our y changes only in the y minus 4, which came from, we could have gotten from our glide vector as well, our translation vector. Very nice. So that means let me alter your homework assignment a little bit. Because like I said, we'll stop there and then we'll finish it tomorrow. So keep the second sheet that came with it. That will be for tomorrow's homework, number 37, not for tonight's. 1 through 1 through 17?
Oh.
1 through 17. Always. Or almost always. Almost always. Okay, so 1 through 17, odd.